this thing, quantum cryptography and the post-quantum cryptography. Okay. So, and in last two lectures, we have covered complexity classes. Okay. So, this is a absolutely fresh topic. So, today we will be starting with that. And so what we will be today covering is what is a classical cryptography and followed by the quantum cryptography. And tomorrow we will be primarily looking at if there is any left out topics for quantum cryptography for today's class, we will be completing that. I hope it will not be. If it is, then we will be covering the post-quantum cryptography. So that is overall kind of a thing that we have. Let me start now. So first, before entering into the topic, I want to just give you some idea about why this is really a very booming field. And just to tell you that the most promising field under quantum computing right now is quantum cryptography. Why? Because seeing a real traction is very smooth for this field. This is the first point, that it adds a certain kind of a business values. In that perspective, I'm telling. Second one is the challenge also, or the kind of that crisis that we have is very high for this field. What do I mean by the crisis? So that all the things we will be first knowing. So the entire introduction I have divided into 4 parts. And today's entire class, we will be discussing about all these 4 questions. We'll try to find out the answers for these 4 questions, right? So the first one is, are we under some security threat? That is, what is the ground for really getting into the quantum cryptography? That is the first thing. Is there any kind of a security threat that we have? Next is, even if we have some security threat, are our existing solutions not well enough or good enough or sufficient enough to handle that kind of a threat or crisis? Third one is, if they are not capable of solving it, then in that case, is there any alternative solution? And the fourth one is, if yes, then what is the solution? So all these 4 questions are there. So first, quantum cryptography has emerged because of introduction of a very well-known quantum algorithm, which was Shor's algorithm. So Peter Shor, he's a mathematician at MIT. So he discovered, or he came up with a fantastic breakthrough of finding the factors of very large numbers in polynomial time using a quantum computer. Now, how that is relevant with a security threat that we want to here analyze is, a lot of classical algorithms that we have, they use the same concept of integer factorization as its core, core module. Okay, so but if that is breakable, then see the hierarchy. So all the classical algorithms mostly rely on our integer factorization. Okay, and integer factorization is something which quantum algorithm, Shor's algorithm, already has solved. Already there is an algorithm to solve it. Now you can understand with a very basic definition of algorithm that if logic is developed, if you give some input, we'll be getting some out, right? So there is kind of a thread that we have. Now the question that you should be asking is, how real the thread is? How real? Is it really very real that we have? Then we should analyze that our next ones. Are our existing solutions not sufficient? The answer is no, they are not sufficient. Why? Because our existing solutions mostly rely on 2 mathematical models. First one is integer factorization. Okay. And the second one is discrete logarithm. So this is integer factorization. integer factorization, and this one is discrete logarithm. They are not any cryptographic algorithms, but they are the fundamental building blocks of any cryptographic algorithms that we have. Now, the thread here is the quantum algorithm that I'm talking about, which is Shor's algorithm, can break both of them. So both IF and DL model is breakable. And also there is a kind of a polynomial time reduction theory with IF and DL. So integer factorization and discrete logarithm, they are almost like the similar thing in terms of reducibility. Okay. What Shor already has shown is with very small numbers like 3 and 5, it is already implemented using Shor's algorithm. So if you give 15 to your algorithm, it will ultimately be able to give you the prime factors 3 and 5. This is already done. Now you might be asking me the question that, but 15 is not a very realistic number that we give, because we mostly give a very large number as my prime number, which I want to further factorize. Then this is a toy model. Then what is the risk here? The risk here is the sharp growth of the quantum hardware that you can see. So it is very much of an anticipated kind of thought that maybe within very few number of years from this, okay, within very few number of years, your existing RSA variants, a lot of RSA or a lot of other current cryptographic or current solution of some security solutions variant will be absolutely under threat. So they are not to be in a form where they can be used further. Now you can see or you can imagine that if you absolutely abort an algorithm or abort a kind of a cryptographic practices, then how many such like aborting the practice you have to do if there are a lot of applications which use that particular solution. Okay, so RSA, say for example, is one algorithm which is a very well known classical public key cryptographic algorithm. I will come into each of these terms like public key, all those terms. This is just an introduction. Okay, so RSA is a very well known algorithm which is very widely used. So this RSA, and there are a lot of variants of RSA. Say RSA 1024, RSA 2048. So these are all some level of, these are some parameters which affect the security level that RSA provides. Of course, if we increase it, say RSA 1024 can provide if X1 amount of security, then RSA 2048 will be providing more security. That is, if it is X2, then X2 is definitely, say, amount of security. Let me write. So amount of security. So if RSA 1024 provides X1 unit of security and RSA 2048 provide X2 amount of security, then definitely X2 will be greater than X1, but computational complexity, computational complexity, let me write it in CC. Okay, so CC for 2048 will also be very high than computational complexity of 1024. That means the time taken in CC will be time taken to compute the complexity for 2048 will be very high than this thing. That is, if you have to get a better, say, better kind of commodity, you have to pay more. Similarly, so if you want to compromise with the security level, you can use RSA 1024, but which will offer some less amount of security, but computational complexity and the like overhead, hardware cost, all these things will be less. But if you are okay with paying more hardware complexity, or if you're allowed to do it in even a bigger amount of time, then you can definitely go for the higher variants. But the thing is that despite all these factors, x1, x2, all these things they are in form of a classical. We know that in classical, this is an exponential concept is there, so it's ultimately some brute force, so it is very difficult. But with the notion of quantum superposition, entanglement, no cloning, all these theories that we have, okay, so this process will be accelerated in almost exponential factor, factor, which will in turn make these things or this breaking or cracking the code or cracking the key in a very fast time. So we say often that some variants of currently used cryptographic solutions might take some trillion number of years in a classical computer. Or what kind of a classical computer? A very powerful, say a terahertz capacity or even more than that capacity one of say HPC I'm talking about. So that is not realistic. That is why we are relying on RSA. That okay, because it is taking trillion number of years, so that means practically that is not breakable. We do not have that much of a time, so it is safe. But quantum true source is coming with a claim that no, it's not any more trillion number of years or million number of years to compute it. Rather, depending on the power of the quantum computer and the whether it's error corrected or not, that is, if it is handled, if it is able to handle quantum errors, or if there is no error, anything you consider, then it will be even it is also possible for some powerful quantum computer to crack that one part in even minutes or even seconds. So this makes it the real threat. And this is real. Why? Because our anticipation is with several variants, maybe because some basic variants are already broken. Okay. And maybe in 5 to say 30 years, whatever we have, no matter how hard it is, they will definitely has a full potential to be broken. That is why this has a lot of kind of a business value right now, because industry and academia all are into it, that how we can mitigate the problem or issues, or is there any alternative solution, because quantum computers here is coming not as a blessing but rather as a curse. So quantum computing is a threat or causing threat to your classical cryptography. Okay, but what is the solution? Solution itself is also in quantum. So that solution is known as quantum cryptography. So I hope right now you've got the context what quantum cryptography is. So quantum cryptography is the means or the way to tackle two new quantum safe cryptographic practices, how to tackle the threats that quantum computers can pose or is posing or has the potential to pose on your existing classical solutions and security practices. That is the context. First, tell me, every one of you got the context that what and why we are here for quantum cryptography? Thank you. Thank you. So now you know that yes, you need it. So there are both research angle of this one as well as the um like uh like kind of for like application angle. That is what I tried to say. So you have to devise those application which is not relying on your existing ones, as well as you have to continuously do some further research that how you can develop alternative solution. One is not to use the current one that you are using. Second one is how you can use something else. Then what to use? That is the next type of question. Now, what we are going to cover today, listen very carefully, what we are going to cover today is that how the security threats posed by quantum computers can be mitigated using quantum, which is called quantum cryptography. And the second one, which we are going to cover tomorrow, is how to tackle the threats issued or imposed by a quantum computer on our classical cryptography using not quantum solutions, using some advanced form of classical solutions. So one is to tackle, we will be using either a quantum solution, which is quantum cryptography, that's how we can solve it using quantum. Second one is how we can solve it using not the existing classical practices, rather some advanced form of classical practices. So that is quantum safe cryptography or quantum resilient cryptography, which are not quantum cryptography. They are not using anything for quantum. They are classical, but they are designed or intended to be designed in a way where it is safe from quantum as well as from any of the classical threats. Okay. So that second part, which is called quantum safe cryptography or quantum resilient cryptography, is also known as, that field of study is known as post-quantum cryptography. None of them are better. Both of them have been thought of, or they are not comparable. I will say that because both are thought of to as our alternative solutions or two completely different approach. One is the advanced form of classical approach, which I will be discussing tomorrow. One is itself the quantum approach. Now both are very different, or both are very difficult. Why? First one, quantum hardware is not matured enough. Quantum cryptography, which is using quantum, that relies on quantum communication, and there also it is facing some challenge in reality in order to like no decoherence, all those stuff. Okay, so they might be needing some quantum repeater. So that is some of the challenges that are associated in order to scale it using quantum. So this is a different challenge. What is the challenge with the alternative mathematical models for like quantum safe one or the classical one or the post quantum cryptography? There it is. Here in the next one, you have to search for some advanced mathematical models. Now, maybe you will be putting a lot of R&D, a lot of things. You will like search for a very hard models. You cannot further rely on integer factorization and discrete log. So you will be taking help of some other advanced form of abstract algebra or something like that. Even after that, like devising it's itself very conceptually difficult. That is the first thing. Second is there is a lot of overhead, computational overhead, because ultimately if you use some algorithm, you ultimately have to encrypt it and then decrypt it as well, right? In order to get the plain text to ciphertext and again from ciphertext to plain text. So that encryption, decryption also you have to do. But with the keys generated or with the kind of algorithms that we have for post-quantum cryptography, in today's kind of whatever till that, whatever research has been done, that is very difficult, or that is very different as well. So that much of an R&D, that much of a like computational complexity or some easy way how to easily do the decryption, because the key sizes are being very, very large there, and the math is itself so difficult there. See, if I give you two very big number and if I ask you to do the addition, that is easy. But if I give you like two things and if the operation itself is not like addition, it's very difficult. With the same key size or even a reduced key size, that operation is going to be computationally a lot more intensive. So all these computational related challenges are there with encryption and decryption, all those stuff is with the post-quantum cryptography. Quantum cryptography is completely a physical process. It relies on quantum physics. Post-quantum cryptography or quantum safe cryptography is completely very, very advanced form of mathematical practices. Both are completely different. So our fourth question, is there a solution? Our third question, the answer is yes. But answer should be, we have two different paths. as a solution. First one is a quantum cryptography. Second one is a post-quantum cryptography. So this is quantum and this is classical. And these are the, of course, solution. Now the entire picture is clear, I guess, with everyone. Okay, thank you. So now on that note, we will start all these things. Now you know the context. Yes. So what is classical cryptography? So you know that it is those who are not very like well versed with the cryptography. You can put your um, effort here. That classical cryptography, it is just the science of encrypting some information. So basically, it's a method of protecting information and communication through use of some codes, so that only those who is the intended receiver can use it and process it. Okay, so that is the process basically. And it is used in order to hide something, hide the very like secret information that you want to hide. That hiding method is known as cryptography, where basically there are two components of it. The first component is encryption, which is that if you have something, so you are a sender and you are a receiver, you have some plain text. Plain text is nothing but the original data that you have. And you want to send it to receiver, then you will be using some encrypting logic, which is like part of the encryption algorithm. So your plain text or your original data through some encryption algorithm will be converted to ciphertext. So ciphertext is non-easily decodable or say non-decodable form of your plain text. Okay. This process to convert from your plain text to ciphertext is known as encryption. Similarly, for decryption, it is exactly the reverse. So now you have the receiver, and when receiver have some information, say some of the ciphertext that receiver has received. Now, how receiver can convert it back to the original plain text? Okay, that algorithm is known as decryption algorithm, and that process is known as decryption. Right? So there are a few security factors that you should be knowing. Let me just write them. If in case you do not know, I'm just writing here itself. The first point is privacy. Privacy means what? That is, it should not be understandable by anyone except the recipient, except the original recipient of the message. Right? So it should be private. That is why information should not be with others. It should only be with the intended receiver. This concept is privacy. Or say confidentiality, whatever you say. Another one is there, which is called availability or data availability. These are just a few terms that I want to talk about. Data availability is, say for example, you are a you have a sender and a receiver, but some way, so you are not able to get the data as a hacker, okay, or as an eavesdropper. But what you can able to do is maybe you are not allowing the receiver to get the information. Okay, so you are creating kind of a barrier so that receiver who should be getting the information in order to do some very useful work or business work will not be able to get your data. That is a kind of a theory for data availability. So your data in cryptographic context should be also available. So it should be private to only the receiver, and it should also be available to the receiver. Okay. Third one is the data integrity. So integrity is, say I have sent this data, sender has sent and data M1 to receiver or wants to send. So receiver got the data, but maybe receiver has received M2 data. So case is like only receiver is getting the data. So its confidentiality is a click. Okay, it's a hit. So receiver is getting the data. So it is available to receiver. So availability wise also it is a hit. But it is not the data which actually receiver should be receiving. What actually he should be receiving is something else, and what he is getting is also different. This process or this problem is known as the integrity related problem, and the feature is called data integrity. Okay, and fourth one is your non-repudiation. So in easy word, this is related to the theory of denial, where denial can occur from both ends. Meaning, say I'm a sender, I want to send you a data. Okay. Now I can say, I can deny that I have not sent you a data. Maybe I have sent you some data. Later, I'm denying as a sender that I have not sent you the data. You are lying. So this is also something to be taken care of. And similarly, it can happen from the reverse order as well. Maybe I have sent you something, but you are clearly denying that, okay, no, you have not received it. So that is kind of a like a denial from receiver's end. And this security factor is known as non-repudiation. Okay. So whenever you want to have a successful security communication, okay, so your secure application should very well take care of all these four factors. First one is the confidentiality, second one is the availability, third one is integrity, and fourth one is non-repudiation. All these four security features you some way have to embed into your security practice. Got it? Okay. Next one is the concept of key that we know. Last point again, sure. Last point is non-repudiation. Non-repudiation means denial. Say I'm denying. Say I've sent you a WhatsApp message right now. So WhatsApp is non-repudiation kind of proof. Okay. You cannot make me fool that, or I cannot make you fool. That is the thing. Say if I have sent you something on WhatsApp, you will be receiving it. Okay. So it should be ultimately in a way where neither sender can deny that he has not sent it or something like that, nor a receiver on receiving it or still it like though it has received it might deny that I have not got this one. Say some banking transaction scenario. Okay. So this can happen. So in that way, ultimately the financial institution as well as the customer, it should be very clear from both the parties. Someone might deny for a transaction. Okay. So maybe bank has taught deducted some amount, then bank is telling that, oh no, I have not deducted the amount. Or maybe you have withdrawn some money from your account, then you are denying that you have not drawn that amount. So this is a denial from both sides. So in security application or very sensitive, security sensitive application, you have to take care of this factor as well. Okay. Next is the key as well as the block cipher. Okay. So key is a fundamental concept for your encryption as well as decryption. Okay. Because mostly what we do is, in order to convert the plain text to cipher text, we use the concept of key. So basically your key is associated with your data, and together they form the cipher text. So you can see this image. Say this is your plain text or say data. This is your key. And finally, with the help of this key, using some algorithm on this plain text, you are generating the cipher text. So your data is definitely important, but your key is even more important than your data. And there are certain features of key where we assume that generally key should be very less, or its key size should be definitely very, very less than the size of the plain text. If plain text is say 1 million bits long, and if your key also is a 1 million bit long, it is generally not kind of a required, or it can be, it is very much desirable. That is the thing. And block cipher is a method of encrypting or decrypting data. Key is used for encryption, decryption, same size as input and output. for block cipher, where you actually divide the entire chunks of data that you want to send in several blocks. Then you are maybe converting through some key that block plain text into block ciphertext. Okay. This is initialization vector. It is another arbitrary number that will be used with the secret key. So this is also a very important factor with which we start with. That is your initialization vector in order to calculate something. So you can just see the diagram. I'll not explain this part. I'll not put a lot of hours here. So initialization vector is kind of the initial content of the register, kind of that. So that with plain text is gives you something, or kind of a, say, encrypted block cipher. Then that encrypted block cipher through some decryption will be converted to the plain text through several processes. Only remember, initialization vector is another component. Just like your encryption algorithm is one of the component for security, decryption algorithm is another component. Similarly, your key is another very important factor. Your data or plain text is another very important factor. And your initialization vector is another very important factor for certain cryptographic algorithm. Okay. Now it is about the types of cryptography, where we generally believe that we have two different types of cryptography. First one is the asymmetric key cryptography, which is also known as public key cryptography. So what is the concept of asymmetric key cryptography? From the term asymmetric, you can understand that there is a difference in symmetry between the keys that are being used. So here the concept is let me draw here. So asymmetric encryption is, say I have 4 users. Okay. Why it's called asymmetric? I'm just describing that. So each user will be having a public key as well as a private key. Each of these users, say 1, 2, 3, 4. So 2 user or user 2 will also have some public key, public 2 and private 2. And they are communicating. So if we have likewise, that means that each user has a pair of key. That is a pair of public key as well as a private key. And public key and private key, they are not same. That is why it is called an asymmetric key encryption. Because the way we do the encryption as well as the keys that is used for decryption, they are not same. They are not in symmetry. Okay. And so if I have, say, 4 users, you can see that for 4 users, how many total number of keys will be there? Each user has 2 keys. Either it's a public or a private. So if I have 4 users, 8 total number of keys will be there. 4 public key and 4 private key. So likewise, the general formula is for n users in a asymmetric key cryptographic practice will be having 2n number of keys. Okay. And how the process is generally done? The process is say A wants to send something to B. Instead of Alice and Bob, I'm just writing A and B. A wants to send something to. So that means A has pub A and private A. Similarly, B also has this thing, pub B and private B. So the concept is when A wants to send something to B, that is during the time of encryption. So A has some data. So A will be using B's public key to encrypt the data that A has. So A will be using B's public key to encrypt the data and send it to B. Then B will do decryption using B's own private key. Okay. Say I know your mail ID and say your say Gmail ID and Gmail password. Okay. So you will be understanding in this way. Now say I want to send you some data. So in order to send you some data, I will be using, of course, your Gmail ID is a public information, but your Gmail password is a private information. specific to you as a user. So I will be using, in order to send some data to you, I will encrypt, say for example, I will encrypt the data that I want to send to you using your mail ID, which is publicly available to everyone. So I will be using a publicly available information from you. Now you, on receiving it, if and only if you are an intended receiver, then you will know you will be having your private key. Now definitely there is a relationship between your private key and your public key. Now based on that relation, so it's kind of a lock and key. So with the only intended receiver with his own private key will be able to unlock the key and get your original data. So we will be using private key of B and the ciphertext. So decryption algorithm on these two in order to get back your original data. So when now you might ask that then in which cases is public key or private key will be used, right? You can have this question when it will be used or why I'm keeping these things then only, because in cases it can also happen that B wants to send something to A, or in a network of users A can also be some receiver of some other communication initiated by some other user. That can also happen. A also has a full provision in a network to be a receiver. So it only depends on the receiver kind of a receiver driven approach, you can say. So when A will be receiver, say now B wants to send something to A. So now B will be using A's public key to encrypt the data that B wants to send to A. And then A will be using A's own private key in order to decrypt the data that B has sent to A. Okay. So this is the essence of asymmetric encryption. Now what will happen? What will happen to the symmetric one? Another one. In symmetric encryption, both sender and receiver share a single common key in order to both encrypt and decrypt the message. So it is the same key that they are using. For each of the communication, that means there will be one single key or shared key, which will be used as a secret key. So that is why symmetric key cryptography is very better to be called as a shared key cryptography, or it is also called as a secret key cryptography. So what is the concept? That means, say now if say I have four kind of users, A, B, C, and D. Okay. Can you tell me that in how many maximum number of shared keys be required in this communication? We have seen for n users, it is for n users, it is basically 2 into n. Now, what I am asking is, can you tell me that in maximum, how many cases there will be or how many maximum number of symmetric keys can be generated? One has told 1, one has told 6. Any other answer? I hope you got the question. Okay, that's the formula. Okay. Can you tell me why it is so? NC2. Can anyone tell that why it is NC2? You can write it on chat. One has told 6, which is nothing but 4C2. Okay, one has told directly the formula n into n minus 1 by 2, and also one has said NC2. I got NC2 is the number of unique keys. That you are telling me the answer. You're telling me the solution. That it is n into n minus 1 by 2, or it is like 4C2, or also like sorry NC2, which is 6. I got that one. I'm asking that why it is NC2. One has given some answer. One is to communicate with n minus 1 is a bidirectional. Absolutely. Each edge needs a key, and in maximum cases, see, just nothing but the number of edges for a complete graph. So in maximum case, okay, if it is a complete graph, That only will give you the maximum number of edges. So A and B can communicate, A and C can communicate, A and D can communicate. Then BC, BD, and BA. I don't need a separate B to A. Why? Because it's a shared key cryptography. So whatever A will be using for B, B will also be using the same thing for communicating with A. So this is one key, this is second, this is third, this one is fourth, this one is fifth, and this one is sixth. So that is why in worst case it will be NC2 number of kind of shared keys that are possible with n users. Okay. Now the next one is, what are the famous algorithms for that? So famous algorithms are for symmetric cryptography, it is DES or data encryption standard, or triple DES, 3DES, and AES or advanced encryption standard. And for symmetric key, it is basically your very well known RSA algorithm and a few of the elliptic curve algorithms. Few other algorithms are there. Now, I will not be putting much time here. I'm giving you the explanation why on symmetric key encryption algorithms, where it is like for the DSA, DES and your AES. I will not be putting much time. Why? Because though symmetric algorithms are also under threat, but what kind of threat they have? Symmetric algorithms, if you know, symmetric algorithms use some sort of kind of a very long approach, or where you do not really you do some sort of repetition. If you know the like circuit for AES, advanced encryption standard, so use a lot of multiple rounds. So through several rounds, you make it computationally hard. So directly, there is no such direct algorithm that can break it, because in order to break symmetric key encryption algorithms, the only cryptanalytic attack that mostly is used is for your brute force attack. Okay. Now with the brute force one, so in that means if you have say AES 128, this particular variant of symmetric key encryption, AES 128. So in worst case, it might take 2 to the power 128 number of such trials in order to break it, which is very high. Which is very high. That is why we know, or we used to call that AES 128 is okay. It's very like secure, you can use it. But in reality, if quantum computers are there, there is another algorithm. There is another algorithm for quantum here, which is known as Grover's algorithm. So Grover's algorithm is not for the integer factorization or discrete log. What it does, if you give it a unstructured database of say n values, then it can find something from the unstructured unsorted database in order of root over of n queries. So that is, if you have an n input, say, so where, and this is unsorted, just remember. So you cannot apply binary search here. So log n time is not possible. So in worst case, what we do, if we cannot apply binary search, because binary search is only applicable on the sorted array, so we have to use linear search. Okay. So linear search of n inputs in worst case will take order of n number of time using linear search. But if you have this Grover search or Grover's quantum search, this algorithm is also ready. So it will make it order of root over of n. So this is not an exponentially faster one like Shor's, but it is ultimately quadratically faster. So the impact also is not that much. So how it will impact is, say AES 256 I'm talking about. So AES 256 using your linear search or brute force attack would take this much of time or this much number of trials. But using Grover, what will happen? It will be root over of 2 to the power 256. What is the value? Root over of 2 to the power 256. 2 to the power 256 whole to the power half. That is 2 to the power 128. So this is significant drop. Definitely this is also significant drop. But only the threat is the quadratic level. That is also very much under threat when you can think of like AES say 256 or AES say 64 or AES 128. They are under threat. Why? Because ultimately AES, that means AES 128 now in Grover will take only 2 to the power 64 number of trials. Okay, 2 to the power 64 in a perfectly available quantum computer with very less noise and all the qubits are working fine, all in that level, it will ultimately can be done on only a 64 qubit quantum computer. So this is also under threat. Anytime we can have the error corrected 64 qubits with available with us. Or the error correction rate will also be like, maybe it's very fine tuned. So we can actually use that. But why we are not focusing much on the symmetric cryptography is, though it is putting quadratically faster something, because if we increase it from AES say 256 to AES next one, which is 512, 512, then using quantum Grover, it will take 2 to the power 256 number of comparison. Then that means 256 qubit fully error corrected quantum computer is needed. So that is why now, because of the development, now whenever you increase number of qubits, so quantum systems are so fragile. So in that calculation in mind, we currently, again I'm telling, we currently are prioritizing asymmetric cryptographic alternative solutions mostly. We are only deprioritizing symmetric key solutions and thinking AES advanced versions are quantum safe because only we realize that maybe that much of a powerful quantum computer is the availability will be difficult. Only on that note, we are bit deprioritizing the solutions for symmetric key cryptographic alternative versions. So some higher variants of AES are still considered to be quantum safe. Am I clear on this part? So that is why our full focus is on the another one, which was the asymmetric key cryptography. So this is under real threat, as you have to say, because symmetric key cryptography can be weakened, but asymmetric key cryptography can be broken. So there is a difference. And few are already broken. And it's easy, comparatively easy, to go for higher variants. So the options are still available with us. It is computationally difficult, but at least, or encryption decryption is very computationally intensive. But still, the model, primary model, we might not need to change immediately. But here, the primary model, which was based on integer factorization and discrete log, that model itself needs to be changed. So that is why this is under very much of a threat. Okay. Now, on that note, let us go further. Now we will analyze bit of RSA algorithm as well as your elliptic curve cryptographic algorithm, which are two very primarily available kind of asymmetric encryption algorithms. So we will be covering this. So RSA is basically invented by three scientists, three mathematicians, Rivest, Shamir, and Adelman in 1978. So it's the first kind of an asymmetric encryption algorithm and very most widely used public key crypto system. And it has a wide varieties of applications where RSA is used, like SSL, PGP, your SMTP, or like maximum communication that you see around us, which relies on some security protocol. They are mostly RSA or ECC. Okay. So the idea of RSA was based on a fact that right now we do not have that much high available or high computationally available kind of a classical computer. which can do it in very less amount of time. So do one thing. Let us rely on finding the factors of a very large integer. So it's kind of a trapdoor function which it uses. What do I mean by a trapdoor function is, if you want to go from left to right, that is easy. So the function itself is an easy function. So it uses a kind of concept of a trapdoor function, where we use that computing f is easy. This is an easy problem. Easy problem means it is in P polynomial things. Now we know what is the meaning of easy and hard and P and NP hard, all those stuff. Okay. But finding, yes. So trapdoor is, say for example, say we often say like that, right, that you can enter into this situation. That is your choice. But coming out of this situation is going to be very difficult. So it's like that. That's why you call it a trapdoor function, where we believe that finding the solution is easy. But finding the inverse of the solution, that is coming back, is very difficult one. So it's a hard problem. And with context of RSA, how it is relevant? Say I have very two large numbers, say P and Q. I've given you these two numbers. And if I ask you that the function is, please, can you find the product of these numbers? No matter how big the numbers are, definitely you should be able to tell that what is the product. And that too in polynomial type. You simply have to multiply these two numbers. But what if I give you this thing? I give you the product itself. Say n into p, p into q is equals to n. So I have now given you n. And instead of like no telling you what's p and q, I ask you that can you please find that what are its two prime components to build up n? Okay. Now you might ask that, okay, in that case also we can find the factors of n. What is so big deal in it? The deal is I will be giving it so big n. Say for example, n is equals to 60. So what can be its factor? Like 1 into 60, 2 into 30, then 3 into 20, then it can be 4 into 15, then it can be what? It can be 5 into 12, and in the reverse order. So all this can be its factor. Now say my P and Q can be either 160 or it can be 230. Oh, there is one more, I guess. 6 into 10. Yes. Yes, I think so. So there can be 230, then it can be 320. So your P and Q can be any of these things, or 415, or say 512, and say 610. So you can imagine there can be 6 possible solutions. Now all of you know that why it is hard wherever there is a brute force. Any brute force makes it difficult. Now here also, even after knowing that, now say, for example, I am using any one of these pair, any one of these things out of 6 as my original P and Q. Now that means you have to do a trial for all these 6 possibilities and have to calculate everything. Then that will give you some key, right? Now that key you have to apply on the plain text. Sorry, on as a eavesdropper. Now right now you're in the cryptanalytic mode. Just think that. So as an eavesdropper, now after 6 different trials, and 6 different trials means computing the entire RSA and everything 6 different times. You have to check that which can be your original key in order to get some valid plain text, because others will not lead you to the valid plain text, right? So in that case, now you can imagine that it initially for calculating f, it was only p into q, which was equals to giving you n. But here it is like computing it in the reverse way, where n is given, and now you are asked to say what are p and q. Then, and only one of that pair, only one will be your ideal solution or ideal p and q. Now say instead of 60, if I give you, say for example, 100-bit long decimal number. It's 100-bit long. It's only 2-bit long. Okay? Or say 100-digit long, whatever you say, decimal number. And that is your n. Now we have to calculate P and Q. Now you can imagine that why it is a trillion number of years and that concept is there. Because it is going to be so big than finding the solutions, because there is a non-determinism. The, the inverse function is why hard, because there is no deterministic one which I can choose. And classical model cannot deal with non-deterministic model. I have told you. They are not built in that way. A deterministic Turing machine can only process deterministic way of thinking. So whenever all these values in a exponential time you have to solve, that again a classical computer fails. So that means a hacker with a classical computer who will come with maybe even a very high or powerful classical computer, even if with that computer, if he tries to break RSA, that is going to be very difficult. So thinking like this and then doing relax all the applications, all the security personals, everything, they're using RSA. Now the thing is that, so and this was in limelight for, and it's also still in limelight for 30-40 years almost from its invention. You can see right now, only by introducing one small quantum algorithm, if I claim that no matter how big your decimal number is, I will be giving you exponentially faster solution. Do you know the power of exponential? If you have say 65536, initially you have to do, in next step I can solve it in 16 times. Then it's 4, then it's 2, then it's 1, kind of that. Or say 8, sorry. Yes, whatever it is. Like way, it will come. It's not actually 8. It is this thing only. In RSS, PQ prime number used or fixed for a RSS session? Yes, that is fixed. So that is the initial note that you have to start with, the P and Q. And accordingly, P and Q are not the keys yet, the private key or public key. They are different. That is why from N, you have to find PQ. Then according to those particular possible values of P and Q, you have to compute the entire encryption and decryption algorithm. That is why it is very difficult. As you can see, this just focus on the last point. RSA keys can be typically 1024 or 2048, or even they are 4096 and 8192. These variants are also there. It's long, but experts believe that 1024-bit keys could be broken in real near future. Remember one thing here, 1024 for symmetric. If it is symmetric, then it is 2 to the power 1024 amount of attack scenarios are required. But for 1024-bit key, the security level that they offer is often very less. Okay. So the offered security level, what do I mean by security level? That is another very important question. So, sorry. So security level means that out of all these keys, everything you cannot really use. They're not usable. Just like the difference between bandwidth and throughput. So bandwidth is something that is available to you, but throughput is the actual utilization, what you can actually utilize. So here also, similarly, say for example, I have a 2048-bit key, maybe only say 120 or say 125 bits of original information or key information is my security level offered. So those bits are actually original. So 2 to the power of that, 2 to the power of say I'm say 1024, I guess it offers 80 bits of security level. So that is pretty less. It is not like the symmetric one where it offered exactly the same bits as your security level. So there is a gap or a discrepancy between the key size as well as the security level being offered. Got it? So we believe that RSA 1024-bit key can be broken in near future. Okay. Another one algorithm here is Diffie-Hellman. I want to put some more time on RSA and ECC. Just a minute. Let me take some. I will do it. So it should be here. Let me add some blank slides. Okay, let me explain it. Let me add some more. Yes. I just want to give you some example on how RSA encryption works. So how RSA works is, before entering into RSA, a small thing I also want to discuss, which is a primary thing for RSA. Okay, I can discuss it here itself. So example for RSA. Say my P is 5 and my Q is basically 11. We only will be using toy examples for any of this cryptographic thing, because in reality, these are a lot of years even to crack. So we will not be taking any realistic value. We are only dealing with some values that is suitable for a toy example, just to illustrate the concept. Okay. So therefore, your N is equals to what? P into Q. That is 5 into 11. That is 55. After that, you have to calculate the Euler. Next step is to calculate the Euler's totient function, which is denoted by phi n. Now, what is the meaning of phi n? Phi n is the number of numbers that are less than n and are co-prime, which also means relatively prime to n. What is the meaning of that? Say, say, uh, say S and N are, S is any number and N are co-prime. What is the meaning of co-prime or relatively prime? I'm explaining that. Say S and N are co-prime, then that will imply that GCD, or greatest common divisor, of S and N, that should be 1. Okay, that is the concept. So, for example, say 5 and 6, GCD of 5 and 6, that is 1. So that means 5 and 6 are relatively co-prime to each other. Okay. So if I tell you that, say, I have to find, say, for 6, this is separate part. I'll keep this thing separate. Say, I have to find 5, 6. So 5, 6 can be, can have how many like factors? What can be the factors? 1, 2, 3, and 1, 2, 3, 4, 5, and 6. So there, what are the terms? So of course it can be not less than 6, because it is strictly number of that are less than n. So this is not possible. Now out of these 5, what is GCD of this thing? 1 and 6. That is 1. GCD of 2 and 6, that is 2. So it's not allowed. GCD of 3 and 6, that is 3. So this one is also not allowed. GCD of 4 and 6, that is 2. So this is also not allowed because it has to be co-prime. Then GCD of 5 and 6, that is 1. So this is allowed and this is allowed. Therefore, 5, 6, that count will cover 1 and 5, but has these numbers. This is not 5, 6. These numbers, and how many like number of numbers that are less than n. So what is the number of numbers that are less than n and co-prime to 6? That is 1 and 5. So 5, 6 is equals to 2. Okay. And also one thing, if you check that 5, say 5 I have given you. So what 5 will be? It is basically 5 minus 1. That is number of numbers that are less than n and co-prime to that are less than 5 and co-prime to 5 are all numbers. Why? because 5 itself is a prime factor, a prime number. Similarly for 7, because GCD of 1 and 5 is 1, GCD of 2 and 5 is 1, GCD of 3 and 5 is 1, GCD of 4 and 5 is 1. So in that way, for prime numbers, it will be, if I have to calculate phi n, that is n minus 1, if n is prime. But what if it is not prime? If n is not prime, then phi n can be calculated as something like this. Let me do it here. Say what I want to do is I want to calculate, say phi 12. It's a small number, we can do a double check. Okay. So in that case, I have to write whatever n is given to me, I have to write it in this way. P1 to the power k1 into, say, P2 to the power k2 into P3 to the power k3, where this P1, P2, P3, these bases has to be the prime numbers, have to be prime. Let us do the calculation here. Say 12 I have to write. That means I can write 3 into 4, but I'm not allowed to write that because 4 it's not prime, 3 is only prime. So instead of writing 3 to the power 1 and 4 to the power 1, I will be writing it 3 to the power 1 into 2 to the power 2, because 3 and 2 both are prime numbers. Okay. So first step is writing the number itself in this form. Second one is what will be the phi n. Phi n will be, if you apply this way, it is n into 1 minus 1 by P1 into 1 minus 1 by P2 into 1 minus 1 by P3. Just apply the formula here for 12. It will be phi 12 is equals to 12 into 1 minus 1/3 into 1 minus half. Calculate it. It's 12 into 2/3 into half. So it's basically 2. That is 4. So if you check also manually, there will be 4 such numbers which will be like this. I guess the number will be 1, 5, 7 and 11. These will be the 4 numbers. You can also double check it. Okay. So all other numbers which is less than 12, from counting from 1, they will be not co-prime. So only these are the numbers which is less than 12 and are co-prime to each other. Now we can go back to the like RSA algorithm. So first step was you will be giving some PQ. So just calculate n equals to P into Q, which we calculated, and it was like 5 into 11, that was 55. Next step was we have to calculate phi n. That is 555. It will be what? It will be 5 to the power 1 into 5 into 11, 11 to the power 1. So it will be 55 into this thing, 1 minus 1 by 5 into 1 minus 1 by 11. So it's 55 into 4 by 5 into 10 by 11. So this will be cancelled out and this is 40. Okay. Third one is you have to choose any random number. So that's on you. You can choose that. So choose E. E is part of your kind of, it's an asymmetric one. So it's a part of your public key. Say I am A, I want to send something to B. So I'm using B's public key. Let me assume that public key is E, which is nothing but, so this is my public key part, public key component. And this is say 3. Okay. So, and you have to choose it such that your GCD of E and this thing, your phi n, that should be equals to 1. And it's also the case with 3 and 40. Fourth one is, now you have to find, yes, absolutely you can do that. Because your P and Q, they are prime number here. So you can directly make it like 5 minus 1 into 11 minus 1. That is also allowed. Okay. Now you have to find your D. Well, the third step is you just need to find an E equals to 3. Nothing else. You have to choose one. Such that E and phi n, they're co-prime to each other. Next one is find your D, which is part of your private key, which you want to calculate, such that your D into E will be congruent modulo 1 for phi n. Just put the value here. So it is 3D should be 1 mod 40. Calculate it in any form. So it will be directly something like D is equals to, if you calculate it, you will be getting 27. Why? Because 27 into 3 will be 81, and 81 is the something which is 1 mod 40. Okay. So after calculating this thing, that means the final pair of public key, let me write here itself. So the public key is expressed as En. That means n was 55. So 3 and 55. Don't worry, we just associate n everywhere, both for public key and private key. And your private key will be nothing but your D and N, that is 27, 55. So this is your public key and this one is your private key. That is how the RSA algorithm works. Okay. Next one, another one I want to, I'm not getting too much of it, but because along with RSA, the ECC or elliptic curve algorithms are another algorithm which is very much a bit of a different structure, but they are also equally vulnerable by like RSA through sure. That is this ECC, or it is called elliptic curve cryptography. Okay, and there are algorithms like elliptic curve digital signature algorithms. Okay, and a lot of like such algorithms which are under threat. So elliptic curve is a set of equations of this is not really related to ellipse or something. So it's kind of an, so elliptic curve is a set of solutions to an equation like this thing. Say y square is equals to x cube plus x plus b. I just want to give you a kind of a flavor of how elliptic curve works. Okay, where a and b are some constants. And we work with like modulo a prime number p. So it's like that. Say for example, y square is equals to x cube plus 2x plus 3 mod 5. So a is 2, b is 3, and that p mod p is 5. So all x and y here in that case, that means all x and y can be ultimate, because ultimately I'm doing mod 5. So what can be the remainders? 0, 1, 2, 3, 4. So that means all x and y can be numbers between 0 and 4, as we are using congruent modulo 5. And you have to find the all xy pairs that satisfy the equation under modulo 5 operation. For that, it's kind of say first case is x equals to 0. I'm doing it a little fast. I'm just substituting and checking that how to get the solution. So this is to this one. I'm just putting the value of x equal to 0 here, nothing else. Sorry, here with a equal to 2 and b equal to 3. So this is equal to 3. Therefore, my y square is 3 mod 5. So no y satisfies. It's not possible. Second one is with x equals to 1. So y square will be 1 plus 2 plus 3 equal to 6. I have a mod 5 that is equals to 1. Therefore, y square is equals to 1. Therefore, y equal to 1 or 4 can be my solution. Why? Because 1 square is equals to 1 mod 5 and 4 square is also 16, which is equals to 1 mod 5. 5 3 is a 15, so remaining remainder will be 1. Okay. That means your points for x equals to 1, you are getting two valid points for y, that is 1 and 4. That means your 1 comma 1 is one solution and 1 comma 4 can be another point. So that means your valid points on curve is 1 1 and 1 4. Say third case where x equals to 2, so y square will be, putting the value, it will be like 8 plus 4 plus 3, which is 15 mod 5 equals to, it is 0. So since y square equal to 0 means y is equals to also 0, therefore 2 0 can be a point. So all these points form the curve under Z5. Z5 means this thing. So all points form curve Z5. Set of all integers under this congruent modulo 5. So if you do addition, if you do whatever, say additive inverse and all those things, if you want to calculate, you have to, again, just every value you have to ultimately, you have to do a modulo 5. So this is set of all integers. Z represents all integers. Okay. This is a like predefined kind of a notation that we use. R for real numbers, Z, C for complex, Z for integers. Okay. So set of all integers under congruent modulo 5. Now the advantage that ECC provides over RSA is ECC uses much smaller key size. So it is very faster and lighter. Okay. So I have to give you one further, this is only the curve concept. Say for example, the elliptic curve discrete log problem. So I'll be using a very simple example for that. So initially for that, you will be given the curve, which is nothing but this equation, say this thing, 2x plus 2. Say I'm taking just a mod 17 here. And a base point on curve will be given. So base point is, say, base point does not mean a point here. It's a it's a pair. Okay. So it's kind of a, say, 5 and 1. So in that case, you have to pick a private key. Concept is you have to pick a private key, which is k equals to, say, 7. And your public key will be nothing but the 7g. That is a scalar, or the private key 7 times g will be your public key. So that is, you have to compute 7g. That is adding g to itself 7 times. Now this g or addition is not really that simple, like we can think of the normal addition. It is here the elliptic curve addition. Okay, it's completely different concept. So elliptic curve point addition, I will just do one step. It's a very lengthy one. It can happen in two ways. The first one is if I'm adding two different points on the curve. So if adding two different points That can be one case. Second case can be, that is, if I double the same. That is, say, my P and Q. So here it's a P and Q are different, and here P and Q are same. So that is, I want to calculate 2P, doubling the same. So slope of the curves under these two cases will be different. So here slope will be m is equals to y2 minus y1 by x2 minus x1 mod p. And here slope will be 3x1 square plus a by 2y1. This is a fixed value mod p. This is the formula. Okay. Where a is from the curve. So here a is from the curve equation. That's from that we are getting the a. What was the curve equation? It was y square is equals to x cube plus ax plus b. This a here is what I am referring. They are the same a. Okay. So in that case, that means your x3 will be nothing but this m square minus x1 minus x2 mod p. Okay. And y3 will be nothing but your m into x1 minus x3 minus y1 mod p. Okay. And also one thing I want to mention, the 7G, the public key. Okay. This is something that will look ultimately like this. Say x dash y dash. So that is what we are interested to compute. Starting from x comma y, we are interested to find some of the x dash and y dash, which will be finally our public key. Okay. So for 7G, it works like that. So 7 means 7 in decimal is equivalent to 111 in binary. That means it is 2 to the power 0, 2 to the power 1, 2 to the power 2. So it can be thought of 4G plus 2G plus G. That will comprise of your 7G. Now G you have, say one value only I will be doing. And that is, say, I want to calculate 2G. Now once you got 2G, that value you have to now use as your G, and accordingly you have to do 2 into 2G, which will be giving you your 4G. Got it? Let me just like get you to 1. Say I want to find 2G. What was my G? Well, my G was 5 and 1. So we are doubling here. Okay, because we are just doing 2 into G. So that means we will be using the slope formula, this thing, this one, right? So it will be 3x square, let me write it, 3x1 square plus a by 2y1 mod 17, where a was equals to 2. So it's basically 3 into 5 square, I'm just substituting, plus 2 by 2 into 1. So this is your m equals to, this is 75 plus 2 by 2, 77 by 2 mod 70. Now how to compute this one? 77 by 2 mod 70. So that means doing this thing like dividing by 2. So this is also not a very normal or a very usual form that we are well aware of. So dividing by 2 modulo 7 means, modulo 17 means, just let me write it in a reverse way. So it means multiply by modular inverse of 2 mod 70. Okay. So instead of dividing, I'm just doing multiply by modular inverse of 2 mod 17. So inverse of 2 mod 17, that means we have to calculate. So inverse of 2 mod 17 is nothing but 9. How it is coming? Because 2 into 9 is basically 18, and which is 1 mod 17. So modulo inverse of 2 mod 17 is nothing but 9, because 9 into 2 is 18, which is congruent modulo 1 mod 17. And this is an inverse element one. Okay. So with 9 only, it is giving you the inverse value. Right? So let me put it directly here. So that means I can rewrite this m. I can rewrite this m as m is equals to 77 into 9 mod 17 dividing by 2, that is half. Right now I'm writing in this way, mod 17. So if you calculate it, it will be something like 13. So your m is equals to 13. So therefore, put the value here for m equal to 13. So you got your m equal to 13. Therefore, your x3 will be m square minus 2x1 mod 17. So that is 13 square, that is 169, minus 2 into x1. So x1 was 5. If you remember, we started with 5, 1 as your g. So x1 was 5. So it's 2 into 5, that is 10 mod 17. So ultimately, it will give you something around 6. 159 mod 17 will be giving you 6. So similarly, if you calculate y3, it will be m into x1 minus x3 minus y1 mod 17. So it will be 13 times, because m was 13. 5 minus 6, that is minus 1. And minus y1, y1 was your 1, that is mod 17. So this one is nothing but minus 13 minus 1, that is minus 14 mod 17. And this is nothing but is the same thing, which is 3. Okay, that means your x3 is equals to 6 and y3 is equal to 3. So if your g was 5 and 1, now you got your 2g, which is equivalent to x3, y3, which is nothing but 6 and 3, this pair. In that way only you have just multiplied g with 2g. Now similarly, if you have to calculate 4g, to calculate 4g, okay, just take your 2g to be 6 and 3, just like your g, then accordingly calculate your 4g. What will your 4g that you have to calculate? Okay, all of you got the basic idea of RSA and ECC? All of you got the basic idea of, okay, both are asymmetric. Both are asymmetric. Both are asymmetric. Okay. We are not discussing about this symmetric key encryption because of the less severity of the quantum attack. And both of these RSA and ECC, they rely on the integer factorization, which is for RSA, and ECC is for discrete logarithm. Okay. These are some few white pages. I will be removing it. Okay. Another one is the Diffie-Hellman or Diffie-Hellman key exchange algorithm. So it's kind of, I'll not discuss a lot more on this one, but it is for the uh, it's another public key encryption algorithm where it uses different kind of keys, where ultimately some sort of man in the middle attack can happen. Okay, but this is another one which is under threat. But the purpose here is different. That's why I added this slide, because it is not like RSA and ECC. They are for the encryption purposes. No, I will not get into more of that. You can only see, like, I haven't even computed for a toy model, not 4G. So it's going to be very different. Like a lot of discussion on classical cryptography have to enter into quantum cryptography today itself. Okay. And cryptography itself is a very vast field of study. So I just covered that part, which is the fundamental ones and the very required versions for the quantum cryptography. I picked up those topics from the classical cryptography. So this is another one which uses the concept of like kind of a concept of an integer factorization for the key exchange problem. Whereas the RSA and ECC was the encryption algorithm, this is a key exchange algorithm. Okay. So now So the quick recap versions already it's a part which is covered. So known threats of quantum algorithms. So quantum cryptanalysis. So traditional public key crypto systems like RSA, DSA, they are breakable by Shor's factoring algorithm because of the efficiently solving integer factorization and discrete log. Can now check whatever is written here. Second one is another beautiful point here is a harvesting attack. Let me discuss it. So any adversary who sniffs and records a publicly encrypted communication may be easily able to decrypt recording using a quantum computer. What is the concept? Say, I am an eavesdropper. Right now, I do not have a quantum computer. So we will be using some communication, but I am an eavesdropper. So of course, I have an evil mind. So what I will be doing is, right now, though I am unable to break the code using a quantum computer because the quantum computers are not yet matured enough, I will be storing everything that I can store. So I'll be creating a all total possible kind of a database. I will be collecting whatever ciphertext I can get. I will be trying to get the keys. I will be like holding some of the blocks of data. Whatever is there, I will be trying to collect that. So that's kind of a concept of a harvesting, where we believe that we will store now and decrypt later. Okay. So when we will be decrypting it, when the quantum computers in a full-fledged versions will be available, then we will decrypt it. So this attack, harvesting attack, is also known as, and this is another attack that can happen through quantum computer, that is store now and decrypt later. This is store now, don't do anything now, only store, then decrypt later. Later attack. And this can also happen through some quantum computers. And why it will be very easy, or why it is called an attack? Because quantum computers can do all the checking in a very exponentially faster time. Okay, so the brute force will be very easy. With quantum computers. This attack is SNDN attack. Okay. Next one is the symmetric key encryption. As I told, that symmetric key, so asymmetric one will be like broken, and this one and hashing functions, they can potentially be broken. So right now, using robot search. So they are right now in a weekend phase. So they can be weekend. Okay. Because, okay, this is a bit wrong. Let me correct it. So AEST 120, it will be 2 to the power 128 operations, but which can be compromised using Grover, and it will be 2 to the power 64. And 2 to the power, how it is coming? This thing. Okay. So root over of this is nothing but 2 to the power half. So this is 2 to the power of 64 only. So it is actually dividing the search space, or the like key search space or attack search space, whatever I say, attack search space. It is actually dividing into two chunks, right? So now it's half. So half, a 50% reduction of search space it is giving using Grover. Okay, great. So next one is this thing. Already have talked a lot about this thing. So Shor also elliptic curve and factoring. So RSA difficulty of factoring, and elliptic curve defilement key extent difficulty of elliptic curve discrete logarithm. So vulnerable to Shor and no mitigation available in classical. That is by increasing, decreasing, nothing like that. If I increase RSA, will key size, will it be more safe? Nothing like that. That is not possible. That is only possible with the symmetric one, but not with the asymmetric. So real life application broken, you can see VPN, MIME protocol, TLS, SSL, XML web service, the public infrastructure lifecycle operations, in transaction for mail transfer, any file transfer protocol, HTTP, everywhere RSA or kind of ECC is used, and all of these applications can be potentially broken by quantum. Similarly, on blockchain also, I will just touch this part. Blockchain, those who are working on blockchain, that you know that most of the encryption feature that we use are based on the PKI infrastructure or the public key infrastructure. Since public key infrastructure is broken or it can be compromised using the quantum computer, so we also see the same things for the blockchain threats as security threats as well. So it is another area. It's a kind of a big vast area where there exists some quantum threat. Why? Because blockchain security fully relies on asymmetric encryption protocols like RSA and ECC or ECDSA, all these algorithms. Okay. Now is the solution. So far, we have seen the methods, the protocols, everything. Now we are entering into the solution. Solution is, as I said, that there can be two different type of solution, either this one or this one. The first one was a quantum resistant cryptography, which is purely classical, which is also known as quantum resilient or quantum safe. And the second one, so this is type 1, and we will be doing also, it is known as PQC. All are equivalent, all of them mean the same. So quantum safe is not really quantum technique, it's rather safing the cryptographic protocol from the quantum threat. That is why the term is quantum safe. Similarly, quantum resilient, how to make the security practices resilient from the quantum attacks. Second one was the purely using some quantum technique which will follow the quantum mechanical postulates. So quantum mechanical postulates and all those terms is here. All these things are here, where we believe that we will secure some communication using quantum superposition and entanglements. So here we encode some information quantumly in quantum states and transmission of particles, also everything in a quantum way. Okay, and the most well-known or say most talked about term in quantum cryptography is this QKD. Now we will learn about only this QKD. So QKD is for quantum key distribution. Why it is very important? First thing is QKD is not for any data. As you know, the quantum key distribution. So ultimately, we are distributing or protecting the key over the quantum communication channel. Because key is safe, mostly my data will be safe because ciphertext cannot be broken without having any clue of what can be my key. For a very large amount of data, where a lot of data are encoded, as well as there are parity and other additional bits. So if there is no clue on the key, or any way that we can detect that some way, one way or the other, my key has been compromised during the transmission or the communication channel, I will simply discard that key. I will not use that key for encrypting my plain text. So if a gibberish information is given to you where you have no clue where are the parity and a lot of stuff for a large chunks of data, you cannot do anything because the data itself will be never kind of decodable without the key. So key is the most important factor for cryptography. So here, instead of focusing on entirely the data, what we want is to protect the key. So that is a quantum key. We will generate a quantum key, then we will distribute the quantum key over from sender to receiver in a quantum safe environment. Got it? And what is the most benefit of it? It is not vulnerable to Shor's and Grover. So quantum cryptography that is not under threat neither by a classical ones nor by a quantum one. So quantum cryptography is both quantum safe as well as classical safe. Why? Because it inherently does not use any mathematics. It uses only the physics. And that also at a quantum level, I remember the first, second, third lectures. So it is in such a level where we cannot really get into. And all the theory like no cloning theorem and quantum teleportation, all those stuff where we believe, and the quantum measurement. So what was the concept? We will be having a quantum system altogether. Through some time evolution, something will happen on the qubits, which is nothing but the same photons. Okay. Now, once what are the features that we have seen? That first feature was no cloning theory. That if you have some quantum state, which is an arbitrary quantum state, I'm coming to the question, just a minute. So if you have a quantum state, which is an arbitrary quantum state, then you cannot really copy that quantum state or clone that quantum state. So as an eavesdropper, if I receive some key in form of a quantum state, okay, then if I try to copy that, that will not be possible. And why it was not possible? Because of the measurement. Whenever you tamper a quantum state in between some transition, or at any point, whenever you are tampering it, it will lose its quantum property. Meaning, whatever original information was there, right now it will be hard, storing some distorted information. So you can never copy them. And whenever you measure them, the quantum state will be some way modified. Okay. That is why man in the middle attack in QKD is not possible. And that is the biggest advantage that quantum cryptography can provide to classical cryptography over classical cryptography. Okay. So, yes. So entangled state, we have seen these things like quantum entanglement has a huge application for in quantum communication. I've told you, because you have to create ultimately the Bell pair, and accordingly the no cloning theorem and teleportation, all this stuff works, which is a primary essence of your quantum communication and quantum networking. Okay. Einstein's of the, we already covered this part. So we have seen that if two objects are separated by a space-like distance, so measurement of first qubit should not affect the state of the other. So, but later it was discovered by him that there is a spooky action at a distance. We have seen that some way there is a kind of a relationship or correlation between the two objects that are separated by some space-like distance. But that is theoretically. But we all also know, we have seen in teleportation, where we believe the concept of quantum entanglement as a primary or the core component of quantum teleportation. Because if you remember, we create the Bell state, entangled Bell state, and where the first qubit of the entangled Bell state was with Alice, and the second qubit of the entangled Bell state was with Bob. Okay, and that, whenever you try to decode it or say regenerate or reconstruct the quantum state, not copying at Bob's end, you used to have, or you definitely will need some classical communication channel, and classical communication channel will follow the theory of relativity. So in that sense, it's theoretical, but in practical cases, since you are incorporating some classical channel also, it will be ultimately obeying the factor or obeying the fact of relativity theory. Okay, that is the speed. Nothing can be faster than speed of light. This is true. Okay, Alice and Bob, you all know the picture. I do not need to get into much of the picture. Alice is the sender, and in general terms, we only use this convention that Alice is the sender, Bob is the receiver, Eve is the eavesdropper. And Alice, with some message, she will be encrypting the message with some key. So message will come and key will come. Alice will encrypt, then send it to over the communication channel. In between somewhere, if might try to get the data, okay, and do all the like confidentiality, integrity, availability, and non-repudiation attack. Okay, and then it will be decrypt at Bob's end. So with the help of some key, Bob will be decrypting it. So the main thing is how to distribute the key. How to distribute the key. And that is what is quantum key distribution is. Okay. So really, I'm not getting into this theory. Okay. This is introducing quantum cryptography. Just not much time here. So there was a concept of where when it was first discovered by, or similar kind of concept was first discovered by Wisner. It is not QKD. It is the concept of a quantum money, where each note used to contain like 20 light trap. And depending on the basis, there used to be four bases here, or optical bases here. Either it's a vertical or it's a horizontal, which represented in this way. It's called HV basis. Okay, where we are encoding two bases here, and it can be either a minus. Let me draw this, or it can be either this thing or this thing. So together it is written in this way, like a multiplication symbol. And this is known as a diagonal basis. Okay. So if I have four possibilities, it can be either a horizontal or a vertical or a 45-degree or a positive diagonal and a negative diagonal. That means four possibilities will total make it 4 to the power 20. That is a trillion number of possibilities, and those are all optical possibilities. Okay. So forging some like quantum money, or say money, if we use instead of a normal note, if we use some quantum note or quantum money, will be very, very different, because these are all the possibilities. So only one, if anywhere there is any tampering, it will ultimately, the data forging will be very easy. So each bill was identified with a traditional number and a database containing the polarization state. Okay. So the concept of, okay, here is the quantum money thing. It's something like this. Something like this. You can see these are all the light trap, what we can give. And four different types of light trap, you can see it over here. So any one of these, all these combinations will be the correct one. So light trap one, maybe this thing, you can see like all these. So this is into like a dependent event. All of them together will have a unique value, and that is the your desired one. So quantum cryptographic protocols to create and validate banknotes, which is impossible to forge. Key idea is arbitrary quantum states cannot be copied due to no cloning theorem, hence it is inherently quantum secure. And it's a milestone towards development of QKD protocols used in quantum cryptography, and this was discovered before the discovery of QKD protocols. Okay. And polarized light and polarization, I'm not, there is of course some unpolarized light through some polarization filter. Whenever it will pass through, it will be polarized. That's it. Okay. And if the two bases, or the like polarization filter and the polarized light has a kind of a same polarization, then it will pass through. If it is completely blocking, that is how like light waves are blocked, depending on that. But if it is horizontal, vertical, and something, maybe I am passing through some this type of thing, then maybe, and I am just putting this light, then maybe 50% will be blocked and 50% will be received, something like that. Okay, because it is some way close now, and seen it's ultimately in the in that waveform, so I'll be getting some probability here as well. So it means it will not be 100% blocked, 50% allowed, 50% blocked. Quantum money, I have told. So if counterfeiter tries to put in a random sequence of this, you know that there is a this times thing. So it is this much, which is very kind of a different one. So it's impossible to forge. These many combinations can be there. Quantum cash and the end of counterfeiting. With quantum money, we cannot do counterfeiting. Done. Feasibility not practically implementable. Why it is not practically implementable? The quantum money, though it was a completely theoretical concept, is it will be very costly. So cost overhead is one of the things. Second one is decoherence. So cost is a challenge as well as decoherence is a challenge, because whenever two like photons will be very closely placed like this, say for example, so it will have an impact from all of them. So due to coupling or decoherence, there will be a lot of like these, their values can be maybe affected, or they can be altered or broken, kind of. Okay, so that can happen. So that is why there is not that much of a feasibility, but maybe with discovery of some strong quantum particle, or say some of the physical machine description, where we are relying on some different form of technology, where which is inherently very less decoherence, or it is kind of a decoherence proof with a very minimum error, then maybe it is feasible. But this concept of quantum money and quantum note was a kind of a mind-blowing theory or a like beginner story for the QKD or quantum key distribution. Can you tell what is the time? Anyone? What's the time now? Do we have some
Three,
time
it's
left?
3:54 then.
The voice is very slow. I cannot hear you, sir. Is it 4 already?
No, it's 3:54 now.
3:54. Okay,
Yeah,
okay. So I have 5 minutes. I have
yeah.
5 minutes. So let me start with a part of it. That's a very difficult question when quantum money can be, because there are so many things. So commercial availability is a factor of the cost over it. But definitely, and that depends on how you want to structure the money itself, quantum money, and how at a gap you want to put it. Honestly, I have no clue, and I don't think with anyone there is any clue on when it can be done. But maybe with only depending on the qubit, their position, what kind of routing, is there any better strategy to put the qubits, or also it can be something like maybe the basis that I'm choosing in the all the 20 light say spaces or that unit, maybe horizontal and 45 plus, putting them in the neighbor maybe will be less decoherence scenario than something else. So a lot of stuff, or say negative will repel, have a repulsive kind of an action, so that will have cancel out. So interference, constructive destructive, a lot of stuff is there. So I don't have any clue on that part, because physical realization of quantum money or how it might look like, there is no such much information available on that. Okay, it depends on a lot of factors. So BB84 protocol, it is the first kind of a protocol for your QKD. There are some advanced versions. We will, but in class we will be only covering the BB84 one. There are a few other variants, which is almost kind of a same thing or kind of a similar thing with a bit of modifications. Okay? So BB is for Bennett and Brassard. So these are the two scientists. 1984 it was discovered. So it's BB84 protocol. Um, and I guess after 15 or 16 years, their paper was accepted. So before that, everyone thought that this is not really practically feasible. So in quantum, everything will happen a lot in a very slow phase. So BB84 protocol, it kind of uses a set of 4 polarizers and 2 bases. Kind of bases are like horizontal, vertical, and diagonal. All these kind of bases. And concept is this thing. So either we will be choosing a HV basis or a horizontal vertical basis, or we will be choosing where we believe that 0 is for horizontal, 1 is for vertical, or we will be choosing the plus minus basis or the diagonal basis. Okay, so this is 135 degree, 45 degree. Whatever you choose, you can actually make 0 as vertical, 1 as horizontal, and vice versa as well. But whatever you will have to choose, accordingly, both you, maybe Alice and Bob, have to agree on that. That is a convention has to be set. But of course, you can change it. But that has to be at least available with Bob. Means you are putting 0 for a like horizontal, and maybe Bob is putting 0 for a vertical. That should not be the case. On at least that much of a consensus should be there. So the step is Alice will first start tossing a coin and generates a random sequence of 0 and 1. Now, if head, if she got a head, then she will be using, because out of 0 and 1, I can get what? I can get either, say, it can be anything like head, tail, head, tail, kind of that. So, if head, then she will be using maybe horizontal vertical basis, and for tail, so this is also horizontal vertical. For tail, she will be using some diagonal basis. The idea is something like that. And each bit is encoded as 0 or 1. Okay. And Bob receives each bit but does not know how to decode it. So he also tosses a coin. So this pictorial representation is a bit easier to grasp. So this is, say Alice wants to send the bit stream 100110000. This is definitely not the key. This is just a bit stream. Okay. So Alice will be tossing a coin based on 100 11000. So maybe coin outcome can be random. So say for example, randomly he is getting head, tail, she's getting head, tail, head, tail, head, tail, something like that. Now basis chosen by Alice, maybe for head it is horizontal vertical, for tail it is diagonal. Let me write it down. Then and say on that note, Bob also does the same thing. Bob also will toss a coin and say that coin outcome is something like head, tail, head, tail, assuming that there is no dependency or no information shared between the coin toss outcome and they are perfectly unbiased and random. So unbiased coin toss. So equiprobable outcome. So okay. So, but one thing should be same for Alice and Bob. That is, if I get a head, I should be using a horizontal vertical, and if I get a tail, I should be doing a diagonal. This mapping was only something that both of them have agreed. Okay. So Bob will be using this thing, same thing. After that, now see, Alice wanted to send this thing. Now, whenever Alice and Bob will be having the same kind of basis, so the light will, this is nothing but the polarization filter. So light will pass through. So we are getting one. Here it is not same. So I don't know what I'm getting. I might get some distorted one as well. As of now, it's nothing that I'm getting. Say now they are again same. So I'll be getting this value. From here, I'm not there, like bases are mismatching. So no information. Here also they are matching. I've got this one. Here also it is matched. So probabilistically, again, we can imagine that if this is the case, then in 50% cases, Alice's and Bob's bases will agree. That means whatever Alice wanted to send, finally, Bob at least will be receiving, or probabilistically, I'm not talking at least or at most, probabilistically or most likely, Bob will be receiving 50% of that thing. But when this is true, when this is only true if there is no eavesdropper in between, it will be 1010. Why? Here it is 1. So here only I'm getting 1, nothing else. Whatever I have here, it is I'm getting here. So see, here it's match. So I wanted to send 0. That is why I'm getting here 0. Here also this is a base match. So I wanted to send 0 and I'm getting a 0 here. So it's a 1000. These are not key. These are not the key. This is just what Alice wanted to send accordingly, whether that has been received by Bob or not. But where I want to end today is, because we are already 4, I guess, and I cannot cover the rest, but it's a bit more. So remember only till today's class where we are ending is we have 50% chance for probabilistically receiving the same basis or the same input or the correct input. Okay. But when this is 50%, only when there is no eavesdropper. A bit of theory slides I'll be adding today, tomorrow, if you want for E91 as well. I will be adding just the difference wherever, but the entire procedure I will not go into much of it because BP84 itself is going to take some time. Then we have to cover it. If possible, I will try to put few information on that, on the other variants of it. But primarily tomorrow, where we will be starting with is that if there is a eavesdropper, then what is the probability or what is the like correction rate for bits being received by Bob? Okay. So in presence of eavesdropper, how Alice and Bob finally work on the bits and what are the other measures that they take to fix and maybe just fix the kind of a misinformation and correct it or finally discard the some of the bits if it is very much of an erroneous, all this stuff, because the practical scenario is not without if, rather it's with if. So with eavesdropper scenario, we'll start with tomorrow. Then we will see the post-quantum cryptography. Tomorrow I will try.
Thank
Try.
you so much, ma'am. So it was a very insightful session, and I would like to add that cryptography is slightly difficult to understand because one needs to know number theory as well as some fundamental knowledge of algorithms. But you have explained it very nicely, and that